Hi, my name is Mohammadamin Ajdari from HPDS Research and Sharif University of Technology. In this talk, I would present why and how to re-architect I/O caches for emerging fast storage devices. This is a joint work of the research team at HPDS Corp and DSN Lab at Sharif University of Technology. In recent years, I/O-intensive and performance-sensitive applications have become popular. Conventional SSDs are no longer sufficient to meet the performance demands. Thus, new storage devices, such as Optane DIMMs and DRAM-based storage, have emerged to provide multi-million IOPS and minimal latency. But they are up to 75 times more expensive, which make their usage difficult. Instead of fully relying on SSDs or emerging devices, I/O caching have appeared as a suitable trade-off, providing high performance of emerging devices and low cost of SSD arrays. As you know, SSD caching on HDDs have been very popular, and with simple search in Google Scholar using SSD HDD cache keywords, we see over 13,000 publications within the past decade. Now the question is, do we need to analyze I/O caching for emerging environments again? Let's look at two real examples of I/O caching in conventional environments and emerging environments. We run a read-intensive workload on 3 enterprise-grade I/O caches. We observed that the 3 caches provide almost similar performance in conventional environments, even though their architectural implementations are totally different. But in emerging fast environments, the performance becomes sensitive to architectural differences. As another example, we observed that lowering the heat rate shows a slowdown of performance in conventional environments, but it improves the performance in emerging environments using the load balancing opportunities between the cache device and fast backend. These results demand a reanalysis of I/O cache architectures for emerging environments. There are 2 main challenges to the analysis and redesign of I/O caches. First, valid analysis requires real measurements and real I/O caches, and real Sani storage I/O caches are difficult to be implemented from scratch. The second challenge is about the variety of behaviors, including read-write ratios and access locality that enterprise workloads have. These 2 challenges require a valid architectural analysis to rely on real I/O caches, use real storage environments, and also cover various I/O patterns. To provide valid analysis on I/O cache architectures, we propose a cache analysis framework with 3 key ideas. First, using industry-grade I/O caches for valid evaluations. Second, generating variety of I/O patterns covering enterprise workloads. Third, a combination of per-component targeted I/O patterns, system-wide profiling, and source code analysis, resulting in deep architectural insight. In our framework, we first divide a cache into 3 regions for internal scalability, read mismanagement, and write handling. Then we run test and analysis steps on them. As an example, let's consider analyzing the scalability. After choosing the cache region, our framework chooses the targeted I/O patterns to run. In the case of scalability, the number of parallel I/O jobs, control access patterns to provide 100% cache hit rate, all read requests, and 4 kilobyte blocks are chosen. During the execution of our synthetic workloads, our framework collects system-wide logs including CPU usage, cache states, device-side bandwidth usage, and other performance-related logs. All of these operations are during online phase. During offline phase, we manually study the source code of the selected region of the cache under test and draw some expected operational flow. By comparing the summarized system logs and the expected operational flow, we provide strong architectural insight. So far, I have shown the motivation behind our work and our proposed framework. I would now present our real system setup and some of our interesting findings. Our storage system has dual-socket 16-core CPUs, 9 Samsung enterprise SSDs for the backend, and enough RAM disk for the cache device. I now explain some of our findings. Our first question is, which architecture for lookup logic provides the most scalable heat request management? We expect 2 parts of the heat request management to have significant impact on performance. the granularity of accessing the metadata table and its locking, and the number of internal threads of the cache. Our analysis on real caches show that locking has two types: coarse-grained, which is locking the whole table, and fine-grained, which is locking part of the table. Multi-threading can also be of two types, with low number of threads and high number of threads. With two types of locking and two types of multi-threading, there are four possible architectures. The easiest and least common one is low multi-threading with coarse-grained locking, and the most complex one is high multi-threading with fine-grained locks. Other architectures have medium complexity. I now show the performance of such architectures. For an architecture with low multi-threading and fine-grained locks, as the number of IO submitting jobs increase, the cache performance is saturated with only 4 jobs at around 340 kilo IOPS. This bottleneck is due to lack of parallel threads. For the architecture with many threads but coarse-grained locks, the performance is slightly better, but it still saturates at 16 jobs and even degrades with more jobs. Our CPU profiling shows a significant increase of spin lock overheads is the source of such performance bottleneck. Finally, for an IO cache with high number of threads and fine-grained locking, we observe almost linear scalability with the number of IO jobs. Our CPU profiling also shows balanced utilization of resources and minimal spin locks. Thus, to design a scalable lookup logic for IO caching in emerging environments, matching the number of threads to the CPU cores and fine-grained locking is essential and provides multi-million IOPS. Our second question is, which promotion logic architectures best suit the read-intensive workloads in emerging fast environments? I go over two promotion policies in this talk, namely always and inhit. Always policy immediately promotes a missed request to the cache, and inhit promotes a block only after n misses of that address. We run workloads with read hits ranging from 10% to 85%. For low locality and high locality that requests are best to be served from one device, the difference of caching policies is small. But for medium locality, delaying the request promotion by one time, that is nhit 2, enables load balancing between the RAM disk and fast backend SSD array, which in turn provides up to 3x higher IOPS than always policy. The third architectural question we ask is, which flushing logic is most scalable in emerging fast environments? In the next few slides, I would show two policies, namely aggressive flushing and lazy flushing. Now let's visualize the aggressive flushing. At first, application is writing groups of blocks to the cache. After a period of time, flushing starts and may degrade performance of the cache, and application writes accordingly. When the cache becomes fully dirty, the pressure increases and may reduce application performance further. Naturally, when the cache does not have any load, the flushing freely happens. The aggressive flushing ensures available cache blocks for fast block promotion, but at the same time, it may reduce cache performance during high loads. Unlike aggressive flushing, lazy flushing has no direct negative impact on performance, as it does not invoke flushing when the cache is on load. When the cache becomes fully dirty, it causes cache bypassing, which translates to load balancing with fast backend SSD array, and it even increases the performance. Lazy flushing only happens when cache is idling. Therefore, lazy flushing not only does not cause cache contentions, it may also improve the overall performance through load balancing opportunities it provides in emerging fast environments. Our real measurements show that flushing policy has very limited effect on average performance. Lazy flushing or aggressive flushing with small batches can provide up to 10% higher IOPS than aggressive flushing with large batches. However, such performance difference is significant in 99.99% tail latency. Lazy flushing or aggressive flushing with small batches are 4.3x better than aggressive flushing with large batches. which greatly improves quality of service guarantee. So far, I have presented 3 findings that help designing a scalable IO cache. For more interesting findings, please read our paper. Now I would show the summary of performance results on the real traces. We observed that our proposed architecture with optimal configurations provide up to 11x higher IOPS over non-optimized architecture running real traces. The improvement in tail latency, that is quality of service, shows a significant value of 2.6x in VDI and over 30x in OLTP bench TPCC. In conclusion, we showed why and how to re-architect IO caches for emerging fast environments. Our proposed architectural design choices improves the average performance and quality of service by over an order of magnitude. For wider impact on community, we have also open sourced the core parts of our cache analysis framework through HPDS Research GitHub page. Thank you for your attention. Now I'd be happy to receive your questions.